So we have a quick one for you this time. It's to show a disjunction introduction, right? So if we're able to deduce anything, any formula, then naturally we can deduce that formula or something else, right? But this can be very useful if you want to build up formula to sort of target a deduction that you're trying to make, right? So let me load up the following sequence that we're trying to prove here. We want to go from P implies Q to be able to deduce P implies R or Q, right? And again, this makes sense. If P implies Q, then we know P must imply Q or possibly anything else, right? And so when we look at this, the first thing that we see is what it is that we're trying to deduce here has an implication at its top level. So working backwards, we can see that an implication introduction is something that makes sense. We want to be able to go from P, that's our assumption, to be able to deduce R or Q, right? Now, again, this is a fairly small one. We can move forwards with the assumption that we make on P, and we have the implication up here. So in a forward step, we have the elimination of that implication, and we now have Q. Now, there's a few different ways to make this final step here, but we're going to go from the fact that we have Q and deduce R or Q, right? So if we select the two of these and we work in a backwards way, you can use the disjunction introduction here, preserving the left or preserving the right in a backward step. And what this is saying is you're going to introduce it into line 4. And so if we were to do this, it preserves the right, it goes through a little bit of details explaining that there's another way to do this, and I'll show you that in just a moment. But here you see the complete proof. We go from assuming P to deducing Q, and then we expand that to R or Q, and now our sort of scope box here has everything that we have. P implies R or Q. Now if we go back one step, a couple of steps here, instead of going in the backwards direction, we can also say in the forwards direction, I want to go from P and just introduce, I need this step first. I went back one too far, so in a forward way we do the implication elimination. But instead of working backwards with the disjunction introduction here, we can work forwards and say, going from Q, I'm going to do a disjunction introduction as well. Now this invents a new term, either on the left side or the right side. And so if we invent something on the right side, look at what this does. It puts Q or, and then some symbol that it just made up, underscore B1. We can try and unify these, but they won't unify in the end. And it's because the ordering of the operators has changed. And if you were to click these two things and try to use this hypothesis, which tries to unify the two there, it says they don't because the structures don't match. Right? Now, if we go back one and we say Q in a forward direction, we're going to introduce a disjunction, but we're going to invent the left side. Now this does match, and what we want to do is unify this new symbol with R. Right? And this is precisely what we can do. So if you find yourself in a proof like this inside of JAPE and you're trying to unify these two formulas that, you know, have invented symbols and then grounded symbols, and you just want to connect the two and say, you know, substitute the real symbol for that invented one, in a forward step, you can say hypothesis here, and it's going to link the two of those together. So you end up with the exact same proof, and the image that you see there is exactly the same. You know, the reason on the right is precisely as, you know, when we use the backwards step for this. But the way that you get there could be a variety of different ways. So keep this in mind when you're doing proofs through JAPE. There may be more than one way to sort of achieve what it is that you're trying to do.